Imagine disproving a fundamental law of physics that everyone believed was absolute truth, only to watch your male colleagues collect a Nobel Prize for your work. This is exactly what happened to Chien-Shiung Wu, an experimental physicist whose precision and brilliance earned her the nickname the First Lady of Physics. But history remembers the men who theorized, not the woman who proved. Today, we uncover the extraordinary story of the physicist who changed our understanding of the universe itself, yet was erased from the spotlight she deserved. Hello and welcome to our channel, where we shine light on the forgotten women who changed history. In today's video, we're exploring the remarkable life and revolutionary work of Dr. Chien-Shiung Wu, one of the most significant experimental physicists of the 20th century. Born in China and later becoming an American citizen, Wu performed the groundbreaking experiment that disproved the conservation of parity, a principle in physics that had been considered an absolute law of nature. Yet despite this momentous achievement, she watched from the sidelines as two male theorists received the 1957 Nobel Prize for Physics based on her experimental confirmation of their hypothesis. Wu's story is not just about scientific brilliance. It's about perseverance in the face of gender and racial discrimination, about changing our fundamental understanding of the universe, and about the systemic erasure of women's contributions from scientific history. Let's dive into the extraordinary life of the woman known as Madame Wu and the Queen of Nuclear Research. Chien-Shiung Wu was born on May 31, 1912, in Liuhe, a small town near Shanghai, China. Her birth coincided with tumultuous times, the final years of Imperial China and the beginning of the Republic. Wu's father, Wu Zhongyi, was an engineer who advocated strongly for girls' education, a progressive stance for that era. He founded the Mingdi School, one of the first elementary schools in China that admitted girls. Wu's father instilled in her a love for science and learning from an early age. Rather than directing her toward traditionally feminine pursuits, he encouraged her curiosity about the natural world. This early support would prove crucial in shaping her future career path, a path that was extraordinarily rare for Chinese women of her generation. After completing her elementary education at her father's school, Wu attended the Suzhou Girls' High School. Her academic excellence was apparent even then, and she soon transferred to the National Central University in Nanjing. There, she studied physics, graduating with top honors in 1934. Her professors, recognizing her exceptional talent, encouraged her to pursue graduate studies abroad. Wu's decision to leave China would prove pivotal not just for her career, but for the future of physics itself. In 1936, with minimal funds but abundant determination, she boarded a steamship bound for the United States, a journey that would separate her from her family for decades due to political upheaval in China. When Wu arrived in America in 1936, she initially enrolled at the University of California, Berkeley. Her plan was to complete her PhD there, but fate had other ideas. At Berkeley, Wu studied under some of the most distinguished physicists of the time, including Ernest Lawrence, the inventor of the cyclotron and Nobel laureate. Lawrence quickly recognized Wu's extraordinary experimental skills and recruited her to work in his radiation laboratory. While at Berkeley, Wu made significant contributions to the study of nuclear fission and became known for her meticulous experimental techniques. Her colleagues began to notice that when Wu was involved in an experiment, the results were invariably reliable. This earned her a reputation as the authority in experimental physics. In 1940, Wu completed her PhD in physics, but despite her exceptional qualifications, she struggled to find academic employment. This wasn't surprising in an era when women, especially women of color, faced significant barriers in scientific fields. The stark reality was that major research institutions were simply not hiring Chinese women, regardless of their brilliance. After completing her doctorate, Wu taught at Smith College and then Princeton University, becoming the first woman instructor in the physics department at Princeton. However, she was not given an office and had to work in a former storage room. Despite these challenges, Wu's research continued to gain recognition in the scientific community. As World War II intensified, Wu's expertise became invaluable to the United States. In 1944, she joined the Manhattan Project at Columbia University, working on the top-secret effort to develop the atomic bomb. Wu's specific role involved researching uranium enrichment and developing radiation detectors. During this critical period, Wu solved a significant problem that had been hampering the project's progress. The process of gaseous diffusion for uranium enrichment wasn't working as expected, and Wu discovered that the uranium was being contaminated by the copper walls of the equipment. This crucial insight allowed the project to move forward. Her contributions to the Manhattan Project exemplified her remarkable ability to apply theoretical knowledge to practical problems, a talent that would later prove instrumental in her most famous work. Although the ethical implications of the atomic bomb would later trouble many scientists involved in its development, Wu's wartime service demonstrated her commitment to her adopted country during a time of global crisis. After the war, Wu remained at Columbia University, where she continued her groundbreaking research in beta decay and weak interactions. It was here that she would perform the experiment that would change physics forever, yet ultimately lead to one of history's most notorious scientific oversights. To understand the magnitude of Wu's achievement, we need to briefly explore what parity means in physics. In simple terms, parity conservation was a principle suggesting that the laws of physics behave the same way regardless of whether events occur as we see them or as if viewed in a mirror. This symmetry principle was considered an absolute law of nature until Wu came along. In 1956, two theoretical physicists, Tsung-Dao Lee and Chien-Shiung Yang, both Chinese-American scientists who had also studied at the University of Chicago, began questioning whether parity was conserved in weak nuclear interactions. Their hypothesis was radical and contradicted established physics orthodoxy. Most physicists dismissed their idea, but Lee and Yang needed an experimentalist of exceptional skill to test their theory. They approached Wu, who was by then renowned for her experimental precision. Wu immediately recognized the significance of the question and decided to postpone her planned visit to China and her own research to design and conduct an experiment that would test parity conservation in beta decay. Working under extreme conditions at the National Bureau of Standards in Washington, D.C., Wu designed an ingenious experiment using radioactive cobalt-60 at temperatures near absolute zero. The experimental setup required extraordinary precision and control of variables. Wu worked through the 1956 Christmas holidays, determined to reach a conclusive result. What she found shook the foundations of physics. When the cobalt-60 atoms decayed, the electrons were emitted preferentially in one direction relative to the nuclear spin. This, in the electron emission patterns, directly contradicted the principle of parity conservation. Wu had demonstrated that, in weak nuclear interactions, nature does distinguish between left and right. The implications were profound. Wu's experiment showed that one of the supposedly fundamental symmetries in nature was, in fact, violated in certain types of interactions. This discovery revolutionized physicists' understanding of the fundamental forces and contributed significantly to the development of the Standard Model of particle physics, which remains our best description of the subatomic world. Wu announced her results in January 1957, and the physics community was stunned. Her experiment was quickly confirmed by other laboratories, and the principle of parity conservation in weak interactions was definitively overturned. The discovery was immediately recognized as momentous. Later that same year, the Nobel Committee awarded the Physics Prize to Lee and Yang for their penetrating investigation of the so-called parity laws, which has led to important discoveries regarding the elementary particles. Wu's name was conspicuously absent from the award. This omission stands as one of the most glaring examples of women's contributions being overlooked in the history of science. While Lee and Yang had proposed the theoretical possibility that parity might not be conserved, it was Wu's brilliant experimental design and execution that proved this revolutionary concept. Without her work, their theory would have remained just that, a theory. The Nobel snub wasn't an isolated incident, but part of a troubling pattern. Throughout scientific history, experimental work, often done by women, has frequently been undervalued compared to theoretical work, predominantly done by men. The theorist proposes, the experimentalist disposes, yet recognition has disproportionately gone to the former. When asked about the Nobel Prize omission in later years, Wu typically responded with grace, focusing instead on the joy of scientific discovery. I wonder whether the tiny atoms and nuclei or the mathematical symbols or the DNA molecules have any preference for either masculine or feminine treatment, she once remarked, highlighting the absurdity of gender bias in a field dedicated to objective truth. Despite the Nobel Prize disappointment, Wu continued her groundbreaking work in physics. Her career spanned over 4 decades and included numerous significant contributions beyond the parity experiment. In 1958, Wu and her colleagues performed the first experimental confirmation of Enrico Fermi's theory of beta decay. This work further solidified our understanding of the weak nuclear force and provided crucial experimental evidence for the evolving standard model of particle physics. Wu also conducted pioneering research on hemoglobin using radioactive techniques, bridging the gap between physics and molecular biology. Her work demonstrated how physics methodologies could be applied to biological problems, foreshadowing the interdisciplinary approaches that would later become common in scientific research. During the 1960s, Wu performed precise experiments that confirmed the conserved vector current theory of weak interactions, another fundamental aspect of our understanding of subatomic particles. Her experimental verification helped cement what would become known as the electroweak theory, which later earned a Nobel Prize for other scientists. Throughout her career, Wu was known for her extraordinary precision and attention to detail. Fellow physicists often noted that if Wu had conducted an experiment, its results could be trusted without question. This reputation for experimental excellence earned her the nickname the Queen of Nuclear Research. While continuing her research, Wu also built a distinguished academic career. In 1958, she was promoted to full professor at Columbia University, becoming the first woman to hold a tenured faculty position in the physics department. She would remain at Columbia until her retirement in 1981. As a professor, Wu was known for her high expectations and rigorous standards. She demanded excellence from her students, but was equally demanding of herself. Former students recall her as tough but fair, and many went on to have distinguished scientific careers of their own. Wu's teaching philosophy emphasized the importance of experimental precision and critical thinking. She believed that physics wasn't just about understanding theories, but about testing them rigorously. Not only has every experiment a right to be performed, she often told her students, but it also has a right to be performed correctly. During her tenure at Columbia, Wu supervised numerous doctoral students and postdoctoral researchers, many of whom were women and minorities. She understood the barriers she had faced and worked to ensure greater inclusivity in physics, though she typically did this through example and mentorship, rather than through explicit activism. Wu was also known for her clear, incisive scientific writing. Her 1965 book, Beta Decay, became a standard reference text in the field, demonstrating her ability to communicate complex physical concepts with precision and clarity. Although the Nobel Prize eluded her, Wu did receive numerous other prestigious honors throughout her career. In 1958, she was awarded the Research Corporation Award, and in 1975, she became the first woman to receive the National Medal of Science, the highest scientific honor in the United States. Wu was elected to the National Academy of Sciences in 1958, the first Chinese-American woman to receive this honor. She also received the Wolf Prize in Physics in 1978, often considered second only to the Nobel in prestige. In 1990, she was awarded the National Medal of Science by President George H.W. Bush. Beyond these formal recognitions, Wu's legacy was honored in other ways. Asteroid 2752 Wu Chien-Shiung was named after her, as were various academic institutions in both the United States and China. In 1990, Sage Colleges established the Madame Chien-Shiung Wu Award to recognize women in science, engineering, and mathematics. Perhaps most significantly, Wu's story has increasingly been recognized as emblematic of the broader issue of women's contributions being overlooked in science. Her case has become a rallying point for those advocating greater recognition of women scientists and has spurred discussions about unconscious bias in scientific recognition. Despite her groundbreaking work and the discrimination she faced, Wu maintained a full personal life. In 1942, she married Luke Chia-Liu Yuan, a fellow physicist and grandson of Yuan Shikai, a former president of the Republic of China. They had one son, Vincent Yuan, who also became a physicist. Wu was known for her elegant appearance and dignified bearing. She often wore formal dresses to the laboratory, complete with pearls and high heels, defying the stereotype of the disheveled scientist. Some have suggested this formal attire was Wu's way of commanding respect in the male-dominated field of physics. Those who knew Wu described her as intensely focused and dedicated to her work. She was not known for patience with carelessness or imprecision, whether in herself or others. Yet colleagues also recalled her warmth and her dry sense of humor, particularly with those who shared her commitment to scientific excellence. Wu's dedication to physics was legendary. During critical experiments, she would often work through the night, catching brief naps on a cot in the laboratory. This intense focus and work ethic characterized her entire career and contributed significantly to her experimental successes. Despite her achievements and status, Wu remained deeply connected to her Chinese heritage. She was unable to return to China for decades due to political tensions between the United States and China, and she didn't see her family again until 1973, after President Nixon's diplomatic reopening with China. This long separation was a personal sacrifice that Wu made for her scientific career. After retiring from Columbia University in 1981, Wu remained active in the scientific community and in advocacy for women in science. She became increasingly outspoken about the barriers facing women in physics and other scientific fields. In her later years, Wu divided her time between New York and California, where her son and his family lived. She continued to give lectures and attend scientific conferences well into her retirement, maintaining her sharp intellect and curiosity until the end of her life. Wu passed away on February 16, 1997, at the age of 84 after suffering from a stroke. Her ashes were buried in the courtyard of her father's Mingde School in Liuhe, China, a fitting return to the place where her educational journey began. Wu's scientific legacy is immense. Her experimental disproof of parity conservation fundamentally changed physics, forcing a reconsideration of what had been thought to be an absolute law of nature. This discovery paved the way for the development of the unified theory of electromagnetic and weak interactions, one of the cornerstones of modern physics. Beyond her scientific contributions, Wu's life story serves as both an inspiration and a cautionary tale. Her brilliance and perseverance allowed her to overcome significant barriers of gender, race, and nationality to make profound contributions to physics. Yet the lack of recognition for her most significant work, particularly the Nobel Prize omission, highlights the systemic biases that have marginalized women's contributions throughout scientific history. Wu's story does not exist in isolation, but is part of a larger pattern of women's contributions being overlooked or attributed to male colleagues. Consider figures like Lise Meitner, who played a crucial role in discovering nuclear fission but was excluded from the Nobel Prize awarded to her longtime collaborator Otto Hahn, or Rosalind Franklin, whose X-ray crystallography work was essential to discovering the structure of DNA. Yet Watson and Crick, who used her data, received the Nobel Prize while Franklin's contribution was minimized. Jocelyn Bell Burnell discovered pulsars as a graduate student, but her supervisor received the Nobel recognition. These cases form a disturbing pattern that extends beyond physics to all scientific fields. The Matilda effect, a term coined by science historian Margaret Rossiter, describes the systematic under-recognition of women's contributions to science, with credit often being assigned to their male colleagues or supervisors. Wu's case is particularly striking because her experiment was not simply supportive work, but the definitive demonstration of a revolutionary physical principle. Without her experimental verification, Li and Yang's theoretical proposal would have remained speculative. Her exclusion from the Nobel recognition cannot be justified on scientific grounds. This pattern of overlooking women's contributions doesn't just represent individual injustices, but has broader implications for science itself. When women's achievements are systematically under-recognized, it reinforces stereotypes about who can succeed in science and discourages young women from pursuing scientific careers. The loss of diverse perspectives and talents impoverishes the scientific enterprise as a whole. In recent years, there has been a growing movement to reclaim Wu's legacy and properly acknowledge her contributions to physics. Books, articles, and documentaries have highlighted her story, bringing attention to both her scientific brilliance and the injustice of her Nobel omission. Educational initiatives now often include Wu in discussions of significant physicists, ensuring that future generations will recognize her name alongside figures like Einstein, Feynman, and Bohr. Museums and science centers have created exhibits about her work, making her achievements accessible to the general public. Perhaps most importantly, Wu is increasingly being held up as a role model for young women interested in physics and other STEM fields. Her story demonstrates both the challenges women in science have faced and the profound contributions they have made despite these obstacles. The reclamation of Wu's legacy is part of a broader effort to correct the historical record and acknowledge the crucial contributions women have made to scientific progress. By recognizing figures like Wu, we not only do justice to their individual achievements, but also create a more accurate and inclusive narrative of how scientific knowledge advances. Chien-Shiung Wu's life and work embody both the highest ideals of scientific inquiry and the persistent barriers that have faced women in science. Her extraordinary experimental skills allowed her to disprove a fundamental principle in physics, changing our understanding of the universe at its most basic level. Yet her exclusion from the Nobel Prize recognition highlights how women's contributions have often been marginalized or attributed to male colleagues. As we've explored in this video, Wu's legacy extends far beyond her parity experiment. Her decades of research advanced our understanding of beta decay, weak interactions, and fundamental particles. Her teaching and mentorship influenced generations of physicists, and her personal story, immigrating from China, overcoming discrimination, and achieving recognition through sheer brilliance and determination, continues to inspire. Wu once said, "I sincerely doubt that any open-minded person really believes in the faulty notion that women have no intellectual capacity for science and technology." Her life and achievements stand as powerful refutation of that faulty notion. She didn't just understand the laws of physics, she changed them. The next time you hear about the fundamental forces of nature or the symmetries that govern our universe, remember Chien-Shiung Wu, the experimental physicist whose precision and brilliance revealed that nature doesn't always behave as we expect, and whose story reminds us that in reclaiming women's contributions to science, we create a more accurate and inspiring understanding of how human knowledge advances. Thank you for joining us for this exploration of one of history's most remarkable scientists. If you found Wu's story as fascinating as we do, please like this video, subscribe to our channel, and share it with others who might be inspired by this forgotten woman who changed history. The images in this video were created using artificial intelligence technology. They are artistic representations intended to illustrate the narration and do not necessarily depict real people, places, or events with complete accuracy. These images should be viewed as interpretative visualizations rather than factual documentation. Some of the sources used in researching this presentation include 1. Noemi Benzer-Koller, Chien-Shiung Wu, Pioneering Nuclear Physicist, Yale University Press, 2021. 2. Tsai Chien-Shiung, Madame Wu Chien-Shiung, the First Lady of Physics Research, World Scientific Publishing Company, 2014. 3. Richard Hammond, Chien-Shiung Wu, Pioneering Nuclear Physicist, Oxford University Press, 2019. 4. Sharon Birch McGrain, Nobel Prize Women in Science, Their Lives, Struggles, and Momentous Discoveries. Joseph Henry Press, 2001. 5. Franklin Eng, The History and Contributions of Chinese Americans. Asian American Studies Center, UCLA, 2020. 6. Zuoyu Wang, Chinese American Scientists, A Transnational History. Harvard University Press, 2018. Thank you for watching.